Hi everyone, welcome back to this digital design by Verilog with Verilog course. Okay, so today we'll discuss about gate level modeling. Okay, so let's start with gate level modeling. So briefly, I have already discussed about gate level modeling beforehand, but today we will dive more deeper into it, and obviously we will do few example problems. So logic circuits can be designed using logic gates. Verilog provide basic gates as predefined primitives. So like basic gates will be available to like AND, NAND, OR, NOR, XOR, and XNOR gates. This will be available to you. Okay, so these primitives, similar to modules, are instantiated directly without requiring any explicit definitions. So Verilog already has these definitions. You don't have to define anything, right? You just have to call them directly. Call them. All logic circuits can be constructed using these basic gates. Verilog basic gates are divided into two categories. One is AND OR gates. Another one is buff NOT gate. Okay, buffer or not gates. Okay, so AND OR gates. These gates have one scalar output and multiple scalar inputs. Okay, so this can have multiple scalar inputs. It can be 4:1 AND gate, 2:1 AND gate. How many of AND you want to do, you can do it. Okay, the first terminal in the list is the output. Always, this is always the case. Like if I write here AND x y z, that means what I am doing is x equals to y and z. That is what this means. So the first element is always the output. So this AND gate, if I have y and z, then I am ANDing it and the output is stored in x. So first element should always be the output. So as it has only a single output, so that's why the first element will always be output. Whatever I write after this, right, you can write three variables here as well. X, Y, Z, W, you can write that. That is within limits, you can write that. There is no restriction. So all the other things will be input. All the other things will just be taken as input. Okay. So that is done. The first terminal in the list is output, while the subsequent terminals are inputs. The output of a gate updates whenever any of its input signals change. Okay, the output of a gate updates whenever any of its input signals change. So that is what we mean. So like basically any of the input signal change, basically if x, y, z, so not x, sorry, if y or z, any of it change, then the output will also change. Okay, so like these are the logic gates that we have in AND OR gate. Okay, AND or XOR gates. Okay, these are the gates that we have available. So like this is how you can call the different gates, right? You can call the gates AND gate, NAND gates, and you don't have to have any separate modules or define the modules. You can directly call the AND NAND gates. Okay, we will go to the code, there we will understand this, don't have to worry about this. And like this is just the outputs and truth tables of the gates when like two inputs are there, right? So like just one thing you have to take care is that like basic thing, if it is 0 and 1, 0 and 1, then this already but you may not know these two. Okay, so let's solve this. In AND gate, we know even if one of the input is 0, then the output will always be 0. So if it is x, right, but if the other input is 0, then the output will be 0. If it is z but the other input is 0, then the output will be 0. For AND gate, we know this for certain. But let's say if both are x, or if one of them is 1 and other input is x, then the output will be unknown. This I have derived previously as well, because I cannot comment if I am ANDing with x. I cannot comment if this x is 0, then 1 and 0 will be 0. If this x is 1, then 1 and 1 will be 1. So I cannot surely say that what will be the result, because they can have two possibilities here. So that's why it is x here. And for all the other cases, it will be x only, because I cannot surely say. In high impedance also, the AND gate cannot surely define what is high impedance, so it will like give output as x. Just one thing I have told you, if one of the input of the AND gate is 0, then the output will always be 0. This thing you have to remember. Okay, for NAND gate, again, like just the opposite, just the complemented version of AND gate. Okay, and OR gate, again the same rule, but here just the opposite, that even if one of the input is 1, then the output will be 1. Okay, so just let me give you an example here. So let's say this is 1 or x. So 1 or x for certain will be 1. No, because I don't care if this is 0 or 1, I don't care, because the result of 1 or anything is always 1. But if I'm doing 0 or x, right, then I cannot comment. There can be two possibilities. If the x is 1, then it will be 1. If the x is 0 or 0, then it will be 0. So I cannot comment what it will be. So that's why here if you see that when if one of the input is 0, other input is x, then it is x. But in case of AND gate, if one of the input is 0, other one is x, then it is 0. So the difference you can see, and like XOR gate also you can do similar logic, you can apply, and XOR gate also you can do. So I don't think I have to explain much. So these are the examples of AND OR gates. Okay, like inside AND OR gates, these are the gates that follow. Okay, now let's come to buffer and NOT gates. So buffer and NOT gates have one scalar input and one or more scalar outputs. So AND OR gates, right, these gates have one scalar output and multiple scalar inputs. Okay, it can have one scalar input as well. That is also a possibility, right? But here in buffer NOT gates, the difference is it has one scalar input. So its input is fixed. Previously the output was fixed, now the input is fixed. It has only a single scalar input, but it can have multiple outputs. Previously it had only single output, but now it has multiple outputs. Okay, so the last terminal of the port list is the input, while all the others are output. So here if I write something like this, like buff x comma y comma z, that means this terminal is the input. Okay, and all of this is the output. That's why I told you to follow the general convention. Generally, like Verilog also follows that in first they write output, then they write input. Okay, that is the convention that they follow. So if I have a buffer like this, then what this buffer will do is basically this input will be z is the input and output is, like I have a two line buffer. This is x, this is y. Okay, so I'll have two outputs. Okay, so like for a 1:1 buffer, you know basic thing. If I'm giving it input 0, it will give it 0. If I'm giving it 1, it will give 1. If I'm giving it x, it will give x. If I'm giving it z, then also it will give x. Because if I'm giving it high impedance, right, it doesn't understand what is the output. That's why it is giving me x. For NOT gate, it will just again just complement it. But for x, obviously I don't know the value, so it will simply give output as x. We'll see this in code. Okay, so that is the work of buffer. Buffer propagates input to the output. NOT gate produces the complement of the input. It produces the complement of the input. Okay, buffer and NOT gates can also include control signals. Okay, like this, right, these things. If I want to enable the buffer or not, just like enable signal. I hope you have studied about enable signal. It is similar to the enable signal. Buffer and NOT gates can also include control signals like buff1, buff0 to propagate the signals conditionally. So if this is high, then this buffer will be enabled. If this is low, this buffer will not be enabled. Okay, so that is what is written over here. So this is the input and this is the buff1. So if buff1 is 0, right, that means the chip is not element. That means the output will be floating basically. So that's why the output is z, high impedance. I don't care if the control is 0, output is always high impedance. Okay, if control is 1, then the output just follows the input. Okay, if it is x, it will be x. If it is z, then also it will be x, because it will be unknown. Because input is high impedance, it does not mean that output will be high impedance. It will be simply x, unknown value. Okay, now if my control signal is x, if my control signal is x, then if my input is 0, then this will be low. What does it mean? It means that it expects a low value. This L means this expects a low value. If input is 1, it expects a high value. That is what this means. If this is x or z, it will always be x and z. That's it. Okay, so you can ignore this fact for now. You can ignore this, you don't have to worry about this. Okay, so this was about the buff1. For the buff0, right, if I have a bubbled control, just it will be complemented. Whatever is here, it will be complemented. For 0, it will be active. For 1, it will be high impedance. That's the difference. Same for this NOT gate as well. For normal NOT gate, for 1 it will be active, it will complement. For 0, it will not be complementing, it will be simply high impedance state. For not if 0, just the opposite. For 0, it will be active. For 1, it will be high impedance. That's it. Okay, we'll come to the like examples. There I will show you. So if I can open the gate level modeling, correct? If I just open the gate level modeling, yes. So it is not opened here. Now I think, yeah. Now let's come to the array of instances. When multiple identical gates are required, an array of instances simplifies the declaration, because like whenever you need a gate, right, you have to multiple times write gate 0, gate 1, gate 2, something like this. It becomes very tedious to manually call these many gates and write the numbers. We can mess up. That's why this array of instances is very helpful. Okay, so what is array? Array is of like similar data type, elements containing similar data type. So I have a array of gates. What we are doing is we are calling a array of gates. That is possible, that we can do, because obviously we will use so many gates, it will become very difficult, right? That's why we have an thing called array of gates, where we can have many NAND gates and we don't have to write them 1 2 3 4. Okay, that is the difference between them. This approach is efficient and reduces coding effort, especially for large designs. Okay, so I will show you in the VS Code, if my VS Code is on. Yeah, so this is the module gate instances. So let me start from the starting itself. Okay, gate instances. So MUT module unit test. First of all, again, the file has changed, so I have to do CD. So CD to my current file location, current project directory. So this will be CD to the current project directory. Okay, now I have to do iVerilog, then gate level modeling, VVP, and gate level modeling test bench. Okay, so like what is this? This is nothing, just like what we're doing, we are instantiating few gates. So this is a AND gate, we're doing the AND of these two numbers, and then we're doing NAND, and like this NAND, right, we can take 3 input as an AND, we can give 2 input as an AND. It is totally possible. Automatically Verilog understands. Verilog has a dynamic nature. Verilog will automatically understand this thing. We don't have to explain it specifically that whether it will be 3 input NAND gate or not. So just name I have given, I can give any name, it doesn't matter. Okay, so let me run this code. Let me show the output. VVP gate level modeling, that one went away. Yeah, this one. So if you see that for this one, it was just a AND of 2 inputs, that is 1 and 0. Okay, you can play around with the values. The AND of 1 and 0 will be 0, so I'm getting a 0. The this is the AND 3 input AND, right? Sorry, this is the first one. So this is the NAND. Then I'm doing NAND of 1 and 0. If I'm doing NAND of 1 and 0, obviously I will get 1. So that is what I'm getting. Then I'm doing NAND of 1 0 1. So again I should get 1, which is I'm getting. It is not throwing an error. It is totally fine. So this first one is the output, and all the others are the inputs. Okay. So I hope you understood this first one. First one is not that difficult to understand. Let's now discuss about the buffer gate as well. Okay. Let's now discuss about the buffer gate as well. So let me call this buffer gate here. This will be MUT. Okay. So now I will call the buffer gate. So if I do iVerilog VVP, now I have this buffer gate, right? So like what am I doing? So like input is 1 and this is just a single buffer. So if input is 1, output should also be 1, which is I'm displaying. Output is 1, which is fine. Here I'm doing not of the input, so it will be 0, which is I'm getting. Then we are using multiple output buffer. This is also possible. So single input is this one is the input, that is 1, and out 4, out 3 are all buffer signals. So I should get 1 on all of these signals, which is what I am getting. Okay, so now you can play around that if you give this x, right, if you give this x, then what you will get. Okay, we cannot give it x like this, we should give it like this. If we see, we are getting all x. Okay, now if this is high impedance, If this is high impedance, you can play around with all the values. I will obviously not show too much, that will just waste your time. Everything comes out to be high impedance. Okay, if the input is high impedance, then the output also comes out to be high impedance. So I think I was wrong here. This truth table, right, needs changing. So in the truth table, like this is from the book itself, I don't know why they have given it like this. If the input is high impedance, then the output also comes out to be high impedance. So like it depends on, I think it varies from compiler to compiler. Sometimes the compiler is X or Z, but ultimately like this anyways is not that important, but it can vary from compiler to compiler. Okay, just be careful of this thing. Okay, so because in the book they have written as X, but here I'm seeing it is high impedance. So sometimes I think it can change from compiler to compiler. Just be careful about that. So now let's come to the controlled conditional buffer, right? If I come to the conditional buffer, so this one will be commented out MUT. Okay, so this one, if I do, so here you can see that I'm assigning 1, but control is 0 right now. If control is 0, that means this is buff 1, buff if 1. If 1 means it will be active when the control signal is high. Okay, and this is how you send the control signal. Okay, so remember, like I forgot to mention here, that here, right, your control signal is actually the second one when you define the control signal, right? Like these are the 4 types of buff and not if. Okay, if 1 meaning that if your control signal is high, then the buffer will be enabled, else it will not be enabled. If your control signal is low, then these buffer will be enabled, else it will not be element. Okay, so active high, active low, same thing. But remember that your control will be here. The last variable will be the control variable, the second last element will be the input, and all others will be the output. So this will always be control, this will be the input, and everything rest, right, rest will be output. Okay, so yeah, I hope you have understood this thing. So yeah, let me come back to the code. So just wanted to mention, so here, right, control signal is 0, and this is if 1. If it is 1, then only this will be enabled. So out 1, I'm expecting Z, right? So that is what I'm getting, out 1 is Z, and control signal is 0 for not get, so it will just complement because it is activated because control is 0 and it should be active while it is low. So control 0 means it will just complement this thing. So complement of out 2 will be simply 1, complement of 1 is 0, that is what I'm getting. Now if I make this 1, then the first gate will be active and the second gate will not be active. Okay, same thing, right? If I make it active, first gate will be active, second gate will not be active. You can play around with this, whatever you want to do, you can do. Okay, so just wanted to show you this thing. Okay, so yeah, that was about the conditional buffer. Let's now move on to the array of instances. So I've explained you array of instances as well. So this is the array of instances. So if I see here, like what do I notice is that let me just call this array of instances. If you see that it is so much tedious for me to write this much, right? It is same as writing this. Okay, it is same as writing this. So like I'm testing these values bit by bit. So what I'm doing bitwise NAND. I'm doing bitwise NAND. What am I doing? So this in1 is a 8-bit number, that is 3. This n2 is a 8-bit number, that is 2. Okay, then I'm displaying the in binary what is in1 and in2, and then I'm doing the bitwise AND. Okay, so if I comment this one and just do this and do this, it will work. What it does is it does the bitwise AND. Okay, it will do the bitwise AND, but can I show it? So first I will do without this, the simple one only. So this one I hope you understand that what I am doing, I am taking the bit 0 of n into bit 0 of in1, ANDing it, sorry, not ANDing, NANDing it, then storing it in bit 0 of out2. That is what I am doing, right? That is exactly what I am doing. So okay, these two are different only. So you will see you are getting the same result. So I am doing bitwise NAND. So if I just compile this code and run this code, so you are getting the same result here. Okay, so this code is equivalent to this much code, right? So that's how simple it becomes. So Verilog also understands whatever you have provided is a 8-bit number. So if you are doing a 7 0, right, it can only do bitwise operation, like AND can only do bitwise operation. But if you want to do it in bigger scale, bigger number, how will you AND it? So this is how you AND bigger numbers, like 8-bit numbers, 16-bit numbers. Okay, so I hope you have understood this. So my in1 is 1 1, in2 is 1 0. So what it does is, what is the bit 0? Bit 0 is 0, bit 0 of this is 1. So 1 and 0 is 0, but I am doing NAND, so I have to take the complement. So the last bit should be 1. Then this 1 and 1 is 1, so but I am doing NAND, so it will be complemented. So the second last bit will be 0. Then again all the rest bits, right, are 0. So 0 AND with anything is 0 only, but as I am doing AND, everything will be converted to 1. So here I can see everything else is converted to 1. Okay, so this is the basic thing. I hope you have understood this point, not that difficult to understand. So like that's how we can declare array of instances, gate instances, array of, I should write this better, gate instances, that is a better name. Gate instances. Okay, so that is how we write this thing. Okay. Okay, so that is the thing basically. So now let me move back here. Okay, so this was about the array of instances. Now we will do few examples. Now like this is the multiplexer design, although I have explained this previously as well. Can you try it out again? Can you design the multiplexer by yourself, and then I will come back with the solution and design the multiplexer from scratch. So let's start with the mux design. So this is the gate level multiplexer design. So we will design a 4:1 mux. So basic things, you know, obviously 4:1 mux will have 2 select lines and 4 inputs, right? So if select line is 0 0, I will choose 0 0, or I will choose I0, else 0 1, I will choose I1 I2. Okay, so these are the logic diagrams. 2 tables are written here. So although I have written this previously as well, we have implemented this. So I'm just showing you the gate level modeling. Okay, how you can call this gate level. This I have already done previously as well. So just showing you real quick. So this is not in the code. Try to code it yourself and try to simulate, right? Try to simulate and code it by yourself. This is the circuit diagram for gate level modeling. And I have also done the mux in the data flow level modeling and behavior level modeling previously. But don't worry, we will understand those later on. So now I hope all this, whatever I have done right now, is cleared. Okay, that's why this slide is here, because I've already written this previously, but at that point of time you didn't knew about gates completely. Now you have all the knowledge about gates. Now I hope you understand this code. Okay, I will not explain this code, just showing you. But what we will do is we will solve the 4-bit ripple carry adder. Okay, so what does a 4-bit ripple carry adder does is a 4-bit ripple carry adder is designed using 1-bit full adders. So it computes sum and carry out, okay, of 4-bit inputs. So bit by bit it computes the sum and carry out. Okay, so basically a 1-bit full adder is A's or B's or Cin. It takes into the account of the Cin as it is a full adder. Okay, and C out will be A into B, Cin dot A's or B. Okay, this already we have done this previously, but now I will implement a 4-bit adder using all this, whatever logic I have told you, using all this. So this is the 1-bit full adder diagram. So I will implement 4-bit, okay, from this. Okay, so like what we are doing is this is a full adder, okay, 1-bit full adder. Okay, so we need to have sum. So sum is the XOR of 3 inputs A, B, C. So you can either do like this, or you can directly write XOR S1 equals to ABC in. Either way works. Okay, why am I doing it like this? Like because we are using 2 input XOR gates, but you can directly write in Verilog S1 A B C. Okay, C. I will show you in the Verilog code. Okay, and then in AND gate we are doing AND of AB, that is here, and storing it in some intermediate value, that is C1. Intermediate value C1. Then I am doing this AND as well, A's or B. A's or B is here, right? S1, in the S1. So this S1 is getting used here, ANDing with Cn, and then I am storing it in C2, and ultimately I am doing the OR of C1 and C2. So that's why I am not using 3 input XOR gate, because this S1 is actually getting used somewhere. That's why to like save another gate there, we are using 2 input, and like this is the most optimized way to code. Okay, this is the most optimized way to code. So this is the full adder, but this is just a 1 bit full adder, but we have to design 4 bit full adder. So how will I design 4 bit full adder? So what we do, we define a module, like now we are designing a hierarchical block, right? We define a module named full adder 4, which has a sum, that is a 4 bit output, which has a C out, that will be 1 bit, which has A and B and C in, which are all 4 bits. C in is 1 bit, okay, and intermediate wires is C1, C2, C3. So what I am doing is I am adding the LSBs, 0th bits, AB and the C in, of course, whatever input carry I will have. So this is the adder, full adder, 1 bit full adder, right? 1 bit full adder. So it can take in 3 inputs, as I have shown you 3 inputs and 2 outputs it can give me. One is the sum, one is the other one is the carry. So I get a output from this 0th bit. So this is the 0th bit of my sum result, right? Then what I will do, as I have got this carry will work as the input of the next sum. So I will show you with example. Let's say I have these 4 bit numbers, right? 1011 and 0100 or 1, something like this. So what we do, how do we add it? So first I add the last 2 bits. So this is 0, 1 plus 1 is 0, and I have a carry. So carry will lie here. Then I will add this carry with the next 2 bits, right? 1 1, again this will be 0, again I will have a carry here, okay? Again this 1 1, again this will be 0, again I will have a carry here, then again it will be 0 and carry will be 1, okay? So ultimately my result will be sum will be 0 and carry out, C out will be 1, okay? So that is how we do the sum, and exactly that is what I am doing here. Same thing, right? I am just passing the previous carry to the input of the next 1 bit full adder, and ultimately the final result I am storing in carry out and sum 3, okay? So I hope you understood, like this is the test bench, okay? So we will go to the code and I will show you this full adder, like not that difficult, I think pretty simple it is. So I will go to the code and show you this. So if I go to the code and then so this is the like module for the simple 1 bit full adder, okay, and this is the module for 4 bit full adder. So now we are doing the hierarchical modeling, so everything is coming into place here, right? We are using gate level modeling and also hierarchical modeling as well. So as I am like calling a module inside the same like file here, okay? So and this is the test bench, okay, this is the test bench. So of course I have, this is a new file, so I have to again change the location. I have to do again change directory. So I will go copy and paste, do cd this, then do I verilog dash o. Then what we have to do, we have to do the gate level modeling, the name dot vbp, then the test bench file name gate level modeling tv underscore tv, okay, then press enter. So it has compiled. Then I will do vbp, the name of the example gate level modeling examples dot vbp, okay. So you can see the output. So if I, let's say I am giving it like 4 bit all zeros and C in is also 0, then C out comes out to be 0 and sum comes out to be 0. If I give some 0 1 1 and 0 1 0 0, that is what we didn't do actually, but still you can understand, right? 1 plus 0 will come out to be, last bit will be 1, then 1 plus 0 again, second last will be 1, then this bit will be 0 plus 1, this will again be 1, and this bit will be 0, like this last bit MSB is 0 and 0, so hence this is 0 only, so we don't have any carry out, so C out is 0. So you can perform this addition. So this I hope you can understand, simple thing only. So that is what we are doing. So I am going a bit fast now because we have built the base, I have explained you everything. Now I hope like whatever code you are seeing, that is all familiar to you, because I have explained everything. Like before this few things were left, but now I hope you have understood this better. I have explained every single thing in the code, okay. So now I think everything is cleared. So how to take the modules, how to call the modules, all those things. So just showing you the output to simulate. So you can simulate, you can play around with the values, you can choose your own values. So that was about the full adder, okay. So let me 4 bit full adder, let me come back to my tablet and let me come back to another topic known as gate delays. So this is another short topic that we must learn. So first of all, gate delays are not synthesizable, okay, they are not synthesizable, like but we have to simulate. They are used for simulation. Why used for simulation? Because in real life gates will have some delay, right? There will be some transition time, like turn off time, turn on time. Like MOSFETs have some transition time, right? So ultimately, what will be the problem? What will be the problem is that although like we have to understand in actual circuit, right, when there will be delay, what will happen to the output. Okay, so we have to simulate the delay, right, then check the output, then check the behavior of the circuit. So that is what we need to do. We need to model the delay so that we actually see in real life there will be delay, right? In real life there will be delay. So we have to model the same behavior in the Verilog code so that nothing is off, because I have designed my code, everything is done. So now I am in the synthesis phase and the code is like I'm converting it into hardware. Once I take a multimeter and take the output from the hardware, I see that I'm getting 0. Okay, that means like that is wrong, right? That is wrong. So that's why you cannot get it. You cannot like that means there is some problem is there might be some delays that you didn't take into factor. So due to those delays, then you have to change your code. So that's why we want to simulate the delay beforehand only, so that whatever changes we have to make, we can make it from the starting itself. Okay, so that is what your delays are for. So gate delays in Verilog allows designer to model the timing behavior of circuits, specifying the time taken for signal transitions like rise time, fall time, something like that. So there are mainly 3 types of delay. One is the rise delay, another is one is the fall delay, then it is the turn off delay. Okay, so rise delay is the transition to logic 1 from any other value. Okay, fall delay is transition to logic 0 from any other value. Turn off delay is transition to high impedance from any other value. Okay, so these are all the delays. Like if it goes from any other value, if it goes to 1, then it is called as rise time. Any other value, if it goes to 0, then it is called as fall time. And turn off time means from high impedance, if it goes to any other value, then it's known as the turn off time. Okay, now delay can be specified in many ways. Single delay applied to all transitions. Basically, if I apply just a single delay, right, then it will understand that rise time, fall time, turn off time all are same, 5 nanoseconds. If I apply 2 delay, then there will be 2 separate like specify separate rise and fall time. So turn off delay is the minimum of these 2. So if I specify single delay, that means 5 will be the delay, 5 nanosecond or whatever is your time unit will be the delay for all transitions, rise, fall, turn off. If I say 4,6, that means I am talking about delay of the rise time and delay of the fall time. So this 4 is the delay of the rise time, 6 is the delay of the fall time. Now what will be the turn off time now? Turn off time will be the minimum of these 2. So what is the minimum of these 2? 4. So 4 will be the delay here. 4 will be turn off time. Turn off time will be 4. Next, 3 delays. Specifies rise, fall, turn off delays independently. So if I write here 3, 4, 5, that means the rise delay will be 3, the fall delay will be 4, and the turn off delay will be 5. Okay, all 3 delays are specified over here. Okay, so that is how you describe your delay. Now there are another way to describe the delay as well, because sometimes, right, some few delays is not consistent. Because if I write here this 3, 4, 5, it may happen that the rise delay, right, due to some condition the minimum value of the rise delay is 2 nanoseconds, but due to some other condition the maximum value of rise delay is 4 nanoseconds. So we need that flexibility. To have that flexibility, we have minimum, typical, maximum values. Okay, purpose is used to model the variability in gate delays caused by IC fabrication. So if you know about bit about IC fabrication, we generally do the simulation using 3 types of values: minimum, typical, maximum. If we are very conservative in nature, so we'll do our simulation in maximum, we'll take the maximum delays. If we are not that conservative but not that like flexible as well, then we will do our simulation by typical, else we will do minimum. If you don't understand this, ignore this. This is for the guys who are in industry, they will understand this thing. Okay, so minimum is the minimum expected delay, maximum is the typical is the typical delay that generally happens, average, and maximum is the maximum delay. Okay, so how do I control it? So we can write like this. Okay, so we can write it like this. This 4:5:6 basically means I am specifying only a single delay. What is a single delay? Single delay is the all, rise, fall, turn off, all delay. So this whole thing is a single delay. If no commas are there, right, this is only a single delay. And this single delay is for everything, rise, fall, and turn off. Okay, but they have their own typical minimum value. So if I set here something like, there will be some simulation procedure while you give the synthesizer, right, you give it some input, please use minimum delays, please use typical delays, please use maximum delays. The synthesizer will simulate according to that. There is a way to give the input, so okay, that will do. So here this is just for single delay where the minimum value is 4, 5 and 6. For all of these three transitions, the minimum value is 4, typical is 5, maximum is 6. Let's come to this one. Here I have a comma here. That means this is for the rise time and this is for the fall time. And the turn off time will be the minimum of these two. If I choose minimum delay, then the minimum of these two is 3. Okay, if I choose the typical, it will be 4. If I choose the maximum, it will be 5. So the turn off, right, turn off will be just the minimum, always individual minimum of the two. So turn off in this case will be 3:4:5, because this is always the minimum out of the two. Okay, and 3 delays, same thing, right, just like I'm specifying for turn off as well, I'm specifying what is the minimum, typical, maximum, and this. Okay, examples of invoking simulator with command lines are options shown below. So if you want, let's say if you want to simulate your code with max delays, so you will write verilog test.v plus max delays. This is not useful to us, we will not use it. So just showing you the syntax. Okay, that much you should know, how you can invoke the max delays, min delays. So if you write here max delays, then it will always choose the max delays. If you write here min delays, it will always choose the min delays. If you write here typical delays, it will always choose the typical delays. That is what we do with delays. So here, like, some basic example is there with delay. So through this example we'll understand about delays. Okay, so let's understand about delays. So this is a delay example. Model description: a simple combinational circuit is defined with the logic equation out A and B or C. Okay, so here what is happening, the AND gate, practically also AND gate may have some delay, right, has a delay of 5 units, OR gate has a delay of 4 units. So ultimately when you will get the output, that is what we are trying to portray. So we have to simulate the same thing. So I write here and I specify the delay #5. That means rise, fall, whatever there is, everything will have a delay of 5. Okay, delay of 5. And OR has a delay of 4. That is what we are trying to simulate. Okay, that is what we are trying to simulate here, EC. Okay, then I have a stimulus model to check the output at 0, time equal to 0, my A is 0, B is 0, C is 0. At time equals to 10, my A is 1, B is 1, C is 1. At time equals to another delay of 10, that means 20, A is 1, B is 0, C is 1, and ultimately at 20 I finish the simulation. So we want to check what outputs we will get, right? We'll check this. Okay, so we are expecting, so I will go to the code and show you like what we are expecting and what kind of output we are getting. So let me just open the delay files first, open the gate delay files first. So if I open the gate delay, this is open now. If I yeah, we are able to see the model. So this is the test bench and this is the model. So basically very simple model. We have AND gate, the circuit diagram is shown to you, like the AND gate has inputs as A, B and output is E. Then the output E is connected to the input of the OR gate and another input C is connected to the input of the OR gate. Okay, and then the output finally we get as out. Okay, so let me simulate this thing. And we will see this in graph. Okay, in graph we can understand this better. Okay, so I have changed my project directory. So again I have to do cd to the new project directory. So if I do cd to new project directory, and then if I do iverilog, right, iverilog o gate, this should be VVP, yeah, then dot testbench, get delays testbench. Yeah, why is there a dot here? This should not be dot. some reason it has become a dot. That is weird. How has it become a dot? This should not be dot. Okay, the name has been changed to dot. I will change the name because the name is not correct. Name should not be a dot here. Should not be a dot. So I'll open this again. Now it's open. Yeah, now it is fine. Yeah, now it is fine. Now if I compile this, it will compile. Now if I do the VBP and gate delays. Okay, it is telling me it has finished its simulation at 40 because this is 10 delay, this is 10 delay. Now after another delay of 20, I am finishing my simulation. So now obviously I want to see the output. I have the waveform, so I want to see the waveform. So I will do gtk wave.exe. If you just press tab, right, automatically that command will come up. Okay, so then I want to open this file, VCD file. Okay, sorry. VCD file gate delays.vcd, yeah, this one. So now this one will open. I'll just okay, this is opening. Yeah, just show you this one. So yeah, now I hope you can see this. So now if I go into the gate delay, inside gate delay, this D1 module is there. So this is wire A, wire B, wire C, wire E and wire D. So initially A was the value. If I just show you, initially A was value 0. Okay, A was value 0 and B was also value 0. But you can see this is all X, because what is E? E is the output of the AND gate. E is the output of the AND gate. So E is X till the time 5. This is the time, what can I say, marker here, right? You can see the marker, it is 5. Okay, E is the time 5. Okay, so this cursor, if I see, is 5. This time is 5. So it does not produce any output till 5, right? Because AND gate itself has a delay of 5, so it will produce only output, like this output A0 B0 is here after 5 nanoseconds. Okay, because it has its own delay 5. Now here, right, if you observe, I'm changing at 10. I'm changing ABC both, everything to at 10 nanoseconds to 1. ABC, everything is changing to 1. But is it reflecting in the E? No. The AND gate is slow, right? It has a delay of 5. So it will get reflected after 5 nanoseconds, that is 15 nanoseconds. So if I move here 15 nanoseconds, I see A has gone from 0 to 1, which is correct, right? As A and B both are 1, so 1 and 1 should give me 1. But after a delay of 5 nanoseconds, it is giving me that delay. Okay, so this is the delay about the Verilog. Now let me explain you about this is done, right? But this in turn goes the input to the OR gate. So OR has a delay of 4 nanoseconds. OR has a delay of 4 nanoseconds. So if I am here, right, C is 0, right? So what happens is, until here, like what is the input to the OR gate? Input to the OR gate at this point of time is X, because it is E or C, right? So all this is X or 0. As it is X or 0, the OR gate output will also be X. Until here also OR gate output is still X until 9 nanoseconds. Why? Because OR gate, because here, right, after 5 nanoseconds, the AND gate output E has gone to 0. But that will not instantly get reflected to OR gate, because OR gate has its own delay as 4 nanoseconds. So at time t equals to 5 nanoseconds, OR gate receives the input as 0 and 0. But it will respond to that after a delay of 4 nanoseconds. So 5 plus 4 is 9 nanoseconds, which is here. So at 5 nanoseconds, I am getting 0, because OR gate has a delay of 4 nanoseconds. That's why from 5 to 4, if you see plus 4, the marker is showing, if you see on the marker, it is showing plus 4. That means there is a 4 nanosecond delay. Okay, so I am at this point. Now there is no change. So there is change at this point. So C becomes 1. So even if one of the inputs of a OR gate becomes 1, whenever one of the inputs of a OR gate becomes 1, the output of the OR gate simply becomes 1. Okay, that is what we know. Output of the OR gate simply becomes 1. But is it happening here? No. Again, at t equals to 10 nanoseconds, C is becoming 1. But again, after a delay of 4 nanoseconds, that is at t equals to 14 nanoseconds, my output is becoming 1. So you can see how much can a delay affect, right? How much changes can it affect? So at t equals to 14 nanoseconds, I am getting 1. Okay, and again, like same thing will happen here only. again all this will go to 0 except a, all this will go to 0. So it reflects, right? So C goes to 0, right? C goes to 0, and at this point of time this is also 1, although C here goes to 0, but this is 1. So like whatever, like at this point, this, right, this point will be reflected after 4 nanoseconds, because I'm at 20 nanoseconds, so it will be reflected here 24 nanoseconds. Okay, so it will be reflected here somewhere here. So if you see at this point of time, both E are going to 0 and C is going to 0. Okay, both are 0, so output should be 0, but again I'm at 25 nanoseconds, the output will go to 0 at 29 nanoseconds after 4 nanoseconds. So this is how it responds, right? This is how it responds. Okay, I hope you understood the point of delay. So I'm not explaining this in between circuit, you can understand this also. I have explained the first part, second part you can understand on your own. Okay, that is the task. Okay, I've explained the whole thing, so I hope you have understood the like delays in AND gates. So that was about the delays. So try to dig it by yourself, try to run the code, try to see the waveform, try to understand whatever, like try to draw by hand first what you are expecting, and see the graph, what the simulation is telling, are those matching or not. Okay, so that is the case over here. So I hope you have understood, like this is what like in textual format, whatever I have explained is written over here. Okay, this is the output that we are expecting. I have shown you the output. So like these are the homeworks that I wanted to give you for exercise 5 from Verilog HDL by Samir Palnitkar sir. So you can solve these questions. Okay, and in the next lecture we will try to understand all these questions and solve all these questions. So I hope you have enjoyed the lecture. If you did, make sure to hit the like button, and I hope to see you in the next video. Until then, happy learning.